All right, today we're talking about one of the absolute best shortcuts in all of multivariable calculus. I'm talking about conservative vector fields. If you've ever been bogged down by a really nasty line integral and thought, there has to be a better way, well, you're in luck. This is the concept that can turn a whole page of work into just a couple of simple steps. So let's get into it.
So, to get us started, just think about this question. Imagine you're calculating the work needed to move something from a starting point to an end point through some kind of force field. You could go the direct route, or maybe take a more scenic, winding path, or even some crazy zigzag. Which path do you think is going to be easier to calculate? Well, the surprising answer is sometimes it makes absolutely no difference which path you take. And that idea, that's what brings us right to the heart of what a conservative field is. So, what does it even mean for a field to be conservative, and why is it such a big deal? Okay, so here's the official textbook definition. A vector field, which we'll call f, is conservative if it's the gradient of some scalar function, f. And this little function f has a special name. We call it the potential function. But what does that really mean, in plain English? It just means that hiding behind that complicated vector field f, there's a much simpler, friendlier scalar function f. If we can find that function, those really hard line integral problems become incredibly easy. The whole game is just unlocking this potential function. And finding that function gives our field two awesome superpowers. First, like we said, line integrals become path independent. It doesn't matter what route you take. A great way to think about this is hiking. Your total change in altitude only depends on where you start and where you end, right? Not the specific trail you took to get there. It's the exact same idea. And second, the line integral around any closed loop, any path that ends where it began, is always zero. Okay, that all sounds fantastic, but how do you know if a field is conservative in the first place? I mean, you don't want to just guess and check, right? Well, lucky for us, there's a super simple, really fast test to figure it out. And here it is, the 2D component test. It's really straightforward. First, you just break your vector field f into its p and q components. Then, as you can see, you take the partial derivative of p with respect to y and the partial derivative of q with respect to x. And the last step, just see if they're equal. If they are, congrats, your field is conservative. It's a ridiculously powerful little test. Now, this isn't just some random math trick. There's a really solid reason it works, and it's called Clairaut's theorem. You probably remember it. All it says is that for a nice, continuous function, it doesn't matter which order you take your mixed partial derivatives in. Since p and q are just the partial derivatives of our potential function f, this test is really just checking to make sure Clairaut's theorem holds. Pretty clever, right? All right, so we've run the test, and it passed. We know our field is conservative. Now for the main event. How do we actually find that magic potential function f that's going to save us all this work? Let's walk through the method step by step. Let's break this down. First, you're going to integrate the p component with respect to x. Now pay attention, because this is the #1 spot where people make a mistake. Your constant of integration isn't just c anymore. It's a function of y, which we'll call g of y. Once you've got that, you differentiate your whole result with respect to y, and then you set it equal to q. This is what lets you solve for g prime of y. Then you just integrate that to find g of y. And finally, you put all the pieces together. That's your potential function. The theory is great, but let's be honest, it's always better to see it in action. So we're going to run through a few examples straight from the study guide. We'll see when that works, one that fails, and we'll even see how this whole thing works in 3D. Okay, here's our first vector field f. Our p component is 3 plus 2xy, and our q component is x squared minus 3y squared. So what's the very first thing we do? We run the test. And here we go. The partial of p with respect to y is just 2x, and the partial of q with respect to x is also 2x. They're equal. So we've got a conservative field, which means we get the green light to go ahead and find its potential function. So we start by integrating p, that's 3 plus 2xy, with respect to x. The integral of 3 is 3x, and the integral of 2xy is x squared y. And what do we not forget? Our little function of y, g of y, our constant of integration. Now for the next step. We take what we just found and differentiate it with respect to y. The partial of 3x is 0, the partial of x squared y is x squared, and the derivative of g of y is just g prime of y. Then we set that result equal to our original q component, which was x squared minus 3y squared. And now look at this. The x squared terms on both sides just cancel out. That leaves us with a really simple equation. G prime of y equals negative 3y squared. We integrate that, and we get that g of y is negative y cubed plus a good old constant c. We found the missing piece. And for the grand finale, we just put it all together. We take our result from the first integration and we plug in the g of y we just solved for. So our final potential function is f of x comma y equals 3x plus x squared y minus y cubed plus c. And we're done.
See? Not so bad.
Let's try another one. This time our vector field f is x minus y, comma x plus y. So you know the drill. First things first, we run the component test. The partial of p with respect to y is -1. The partial of q with respect to x is +1. Well, -1 is definitely not equal to +1, so the test fails. This vector field is not conservative. So what does that mean for us? It means no shortcut, no potential function to save the day. For this field, the work you calculate absolutely depends on the path you take. In physics, you'd say this field has curl, a kind of rotational quality to it. And for us, it means if you have to find the line integral, you've got to do it the long way. Okay, let's step it up a notch and see how this works in 3 dimensions. Now, this vector field might look a little more intimidating, but the logic behind solving it is exactly the same. We just have to add one more little step to our process. So here's a quick rundown of the 3D process. We still integrate the first component with respect to x, but now our constant is a function of both y times and z. Then we differentiate that with respect to y and match it to the y component. That helps us find part of g, but it leaves us with another new unknown function, this time just of z, which we'll call h of z. Finally, we differentiate everything with respect to z, match it to the z component, and that lets us solve for h, which in this case just turns out to be a constant. And after we put all those pieces together, we get our final 3D potential function. F of x, y, z equals x times y squared plus y times e to the 3z plus our constant c. See? The method scales up perfectly. So what's the big takeaway here? This isn't just some neat theoretical trick. It's a seriously practical tool. The next time you're working through your problem sets, keep an eye out for these. Learning how to spot a conservative field means you can now tackle a whole bunch of really tough problems with way less effort. It's a total game changer.